So if you are interested in giving a talk, upcoming talk, please click on this Google form and fill it out, and we can get you scheduled for this fall. We really appreciate it. And then also today, we'll also put this link into the chat, but any questions, please put into this Word Google document or discussion document, and you can ask any questions to the presenters here anytime during the talk or even after. So please go ahead and use this for questions versus the chat box. It's a little bit easier to have back and forth. Okay, and then that's all I had. So we'll pass it over to Dr. Richter.
Great, Yaga, I'm going to make you a presenter. And
Great.
Just to remind everyone that we are recording.
Great, and I'll put my presentation in full screen, and can you just confirm that you can see that?
Yes, we can.
Excellent. Great. Well, my name is Yaga Richter, and it's my pleasure to be here today and talk to you about subseasonal Earth system prediction framework with CSM2 and its application to the January 2021 sudden stratospheric warming. This is work that's been done with several people at NCAR and also partnering organizations, including Sasha Glanville, Nick Davis, Jim Edwards, Lam Tao Sun, Hu Kim, Hayami Kim, Julie Caron, Steve Yager, and a few others. It's been a big effort, and we really appreciate the help. Okay, so I'm going to talk about three things today. First, a little background, motivation, and also work we've done with CSM1, or the Community Earth System Model version 1. Then the main part of the talk will focus on our newest model, is CSM2 with KM6, which is a low top model, and CSM2 with WACM6, which is the high top model.
Excuse me, are you talking about the second slide? I'm only seeing the first one.
Yeah, so I clicked on my second slide and you're not seeing me advancing, right?
I'm not. I don't think it doesn't look like it's in the presentation mode.
Okay.
I don't know other people have seen. This is what I've been seeing. It's not in the present. Okay, this is good.
It should be, see.
Yes.
Great.
This is outline. Yeah.
Perfect. And then lastly, I'll talk about the January 5th sudden stratospheric warming. Okay, and let's see, I'm going to the next slide, and yes, you can see that, right? Okay, so a little background and motivation. So NCAR, the National Center for Atmospheric Research, as the name implies, is very much a research organization. So we do not do operational forecasting per se. Our focus is on research. And subseasonal prediction is a relatively new area of research, and we want to focus on understanding sources of predictability using the Community Earth System Model, CSM1. And we have a history of contributions with this model to obviously the IPCC and some of Six Sigma simulations, but CSM1 also contributed to the NMME, so the seasonal forecast, and CSM1 was used for the DPLE, or the Decadal Prediction Large Ensemble, was showing really good skill for NAO prediction in particular. So we started our subseasonal prediction efforts with CSM back in 2015, and I actually had a joint project with Judith Prowitz and NOAA that focused on the role of Stratosphere on initialized prediction, and that was the first effort that we ever started at NCAR on the topic. And when we did this, we really wanted to have a study that showed us how much does the stratosphere matter for week 3 for subseasonal forecast and for the NAO. And we set up our system with 2 versions of the model, one utilizing our default atmospheric model, the 30-level CAM, and then a higher configuration, so with the model with a higher top with 46 levels that had a much better representation of the stratosphere. So in climate mode on the right here, I'm showing what the tropical winds look like in those models, and top panel's observations, obviously showing the tropical QBO. And the default model does not have a QBO, does not have any non-orographic waves. So you have persistent easterlies, and this higher top version of the model reproduces the QBO, not perfectly, but it's much better than what the default model does. And we ran all the hindcasts in coupled mode, so our model has a fully coupled land, ocean, and sea ice components. For all our work, we followed the subseasonal protocol, and for CSM1, we did hindcasts from 1999 to 2015, 10 ensemble members with the default model and 10 ensemble members with the 46-layer model. We used ERA interim as initial conditions. For the atmosphere, we used crew NCEP for land and JRA 55 forced ocean hindcasts, and I'll call this data set JRA 55 FO or GEO, sometimes data ocean in the future. It's the same ocean initialization as we used for decadal prediction, which has been shown to be really the, this is the state of the art what they're using for decadal prediction. And so here is the surface prediction scale of those versions of the model, and there are two main outcomes of that. First, we found that the overall scale of CSM1 is comparable to the NOAA CFS V2 model, and you see that in the left hand plot here. This is over global land, 2-meter temperature, and the NOAA CFS V2 model is here, and then the two versions of CSM1 are a little bit over to the right, and you see for all of the seasons their scale is comparable. You can find small differences, none of them are statistically significant, but overall CSM1 is doing really well. And in addition, if you add the two CSM models to the other SubX models to create a multi-model mean that consists of 9 members, this last column here, then the multi-model ensemble is even more skillful than the ensemble with 7 members or any one of the individual models. And the other finding that we found, though, however, which was highly disappointing, is that there was no overall scale difference at the surface between the 46 level and the 30 level CSM1. And you see that on the left plot with surface temperature, and you see that on the right for the North Atlantic Oscillation, or the NAO. So at week 3, CSM1 has really good NAO prediction skill, so we have an ACC of 0.5. But if you compare the blue and the gray bars, you see that the addition of a well-resolved stratosphere did not give you any additional skill. But the 46 level model does cost 50% more. Okay, and we only done hindcasts with CSM1. And here's one additional skill metric. So people also are curious, how does the stratosphere, in particular the addition of the QBO, affect MJO predictability? And the answer is, at least in our model, it does not. So in the plot in the right, I'm showing the MJO predictability for East QBO phases and West QBO phases, and they're two different, and there is no difference. And if you looked at this plot between the two versions of the model, there is also no difference. And what I suspect it happens that although our low top model does not simulate the QBO and it doesn't have a great stratosphere, when you initialize it, the stratosphere is very slowly evolving. So the initial conditions hold pretty well into the week 3-4. So although what you see here is zonal mean wind between 10 south and 10 north, and composite on the particular QBO phase. So you do see the degradation in the 30 level model. However, the sign of the anomalies is correct. And I think as you went out to seasonal timescales, the scale between these models might continue to diverge. But in those earlier timescales, we really have not noted any notable difference between the model versions. Okay, so now moving on to CSM2. CAM6 and CSM2 WACAM6. So that's our newest version of the NCAR model that was released in June 2018, mainly for the IPCC, the ERA6 simulations. And both versions of the model have 1 degree horizontal resolution, and they have prognostic aerosols. And the low top version is still at 40 kilometers with 32 levels now. It has only orographic gravity waves, and no interactive chemistry. And we ran a full reforecast set following the SubX protocol with this model, and we started running it in real time in April 2021. So yes, just last month. Now CSM2 WACAM6 is the most complex model that we have. It has a top at 140 kilometers, 70 levels. It has non-orographic gravity waves from convection and fronts, and it has fully interactive tropospheric and stratospheric chemistry. which means that the cost of CSM to WACM compared to CAM is 8 times more. So for this reason, we are only able to run a 5-member ensemble for reforecasts, and we could only run start dates between September and March. So focusing on the Northern Hemisphere winter season, that's the season where we believe the addition of the stratosphere and the upper levels atmosphere would have the most impact anyway. And we've been running real time since September 2021, and we've been contributing this model to the NOAA CPC Week 3-4 outlook since then. And since the hindcasts with this model ended in March, then now we transition to contributing the low top model to these forecasts. So I'm going to go through some basic metrics. Oh, before I do that, let me tell you a little bit about the initialization, because it is different from CSM1 and it's different between the two models. So the land, we use CFS v2 and we force a CLM5 standalone model, and that's how we get our daily initial conditions. For CSM2, we keep going with the JRA 55 data ocean, and we're using CFS v2 atmosphere instead of era interim because we cannot get era interim in real time, and we can get CFS v2. And we simply just interpolate it to the CAM grid and get our atmospheric initial condition. Now, WACM is a lot more complicated, and the reason is because our top is at 140 kilometer, and there's just simply no reanalysis that we can take and interpolate onto our model grid. So what we actually have to do is run WACM nudged to a reanalysis, and we are very thankful to be getting the MERA and the FPIT data. FPIT stands for Fast Processing for Instrument Teams, so that's basically a fast version of MERA that we can get within a few hours delay. So we can run this model in real time. So we use a 1 hourly nudging timescale to nudge our atmosphere to MERA. And we're also nudging the ocean because we didn't have JRA 55 in real time. So the ocean is also, the forcings from MERA are also nudging the ocean. So there are slight differences in the atmosphere and in the ocean initial conditions between the models, and the land stays the same. So just to give you an idea how much different the ocean state is, what I have here is correlation relative to HAD ISSTs for JRA 55 DO on the left and for the WACM force ocean on the right. And you do see that the correlations are very high, close to 1 almost everywhere, except in the tropics. In the WACM 6 SD simulations, the correlation coefficients are a little lower. And you'll also see this in the plot on the bottom where we plot the ENSO index versus observations. So the JRA 55 forced ocean is doing a really good job tracking observations, and WACM not always. Sometimes, for example, in the year 2016, our ENSO index seems to be a little high. Actually, it's high for a lot of the cases. But in any case, that's the best that we can use for that model. However, it does not really seem like that affects our skill very much. So what I've plotted here is all our NCAR model versions and looking at skill for weeks 1, 2, 3, 4, and 5, 6. And in addition, we know that the ensemble size matters, and we only have 5 ensemble members for WACM. So we subsampled some of the larger ensembles to also include 5 members. That's why you're seeing 5 bars here. But the main message is, if you look closely at any of the top or bottom panels, is that skill across all NCAR models for surface temperature is very similar. So we used the Fisher Z-transform to try to assess if there are any statistically significant differences between these models, and the answer is no. It could be partially that there isn't enough samples. It's only a 20-year hindcast set. But overall, you see that the models are performing very similarly, and likely the small changes in the initial conditions between the models are not causing much issues. And you see a similar thing for precipitation. Obviously, the skill in precipitation overall is much lower than for surface temperature, and especially in June, July, August, where the skill is often below 0.1, meaning there's really no skill in precipitation in the summer season in North America, or even over global land. But it is very consistent with all the other models, NOAA model, ECMWF, etc. These numbers are not any lower. And looking at spatial patterns, so we thought maybe there would be some differences in spatial patterns where the skill is between the models, because they do have different features. One has a stratosphere, etc. But the answer to that is also there are very few differences between the model versions. So on the left here, you have the ACC for DJF 2-meter temperature in CAM6, which is kind of what is going to be our basic model. And you do see skill declining as you go into weeks 5, 6. And if you look at differences from CSM1 and from CSM2 WACM, there are very few regions where there are skill differences. There are some, and most likely we cannot really track them to any particular change because there are physics differences between CSM1 and CSM2, as also differences in initial conditions. So there may be something to explore further, but in my eye, these differences seem pretty small. And similarly for precipitation, on the top left and the left column is the skill. And again, the model is not very skillful, especially after week 3, 4, and the differences in precipitation between the different model versions are very small. There's the MJO and the NAO, because those are the key quantities of interest for subseasonal prediction. And here you're seeing a little bit more difference, especially for the NAO. So CSM1 still seems to have the best skill. And we saw that in previous plot at week 3, ACC is 0.5 and even average over weeks 3, 4. And for 5-member ensemble, CSM2 WACM also does seem to have pretty good skill. But again, if we did statistical differences, they're not showing anything, but there is a little indication here that there may be a little bit more diversity in the predictability of the NAO between the models, something we haven't had much time to investigate in detail. But overall, all the models are doing well. And of course, if you have more ensemble members, your skill is going to be higher. On the right here, I have the skill of the MJO. And most of our model versions predicted out to day 25, and there's not a whole lot of difference. And the one thing I will mention, when you run CSM1 standalone, the MJO is very poor, and it has been improved in CSM2. So when you run it in climate mode, it's improved, but we're not seeing any improvement in predictability, which I think is an excellent research topic. Again, something to work on in the future. So you might be curious whether there is a better representation of sudden stratospheric warmings between the low top and the high top model. Again, we didn't find this in CSM1 to our surprise. And it seems to be the similar situation in CSM2. So what I'm showing here is a composite of the 14 sudden stratospheric warmings that occurred between 1999 and 2020. And I'm showing here polar cap geopotential anomalies. So what you should see is that these anomalies coming down after a sudden stratospheric warming to the lower stratosphere, and then also you see a signal at the surface, especially in observations here. And if you look at CSM2 WACM, the correlation coefficient squared with observations is 0.8, and it's only a little bit lower for CSM2 CAM6. So a model that really does not have a good stratosphere, you can see it is grayed out here because there's just no levels, and even the levels, the top levels have very coarse resolution, but somehow this does not seem to be affecting our polar cap geopotential anomalies and how they compare to observations. There is a little degradation in the low top model, but it's not very big. So we have a lot of data available for the broader community from these two model versions. So in addition to SubX P1, P2, P3, which are the priority 1, priority 2, and 3 variables, we also have full 3-dimensional output on a daily basis of U, V, T, omega, Q, relative humidity, UQ, VQ, Z3. These are just variables different researchers over time tell us that they might want to look at. We also have 6-hourly tropical cyclone tracking output. We have additional land and ocean output. It's a lot of output, and it's slowly being uploaded to the NCAR Climate Data Gateway. I know out of this morning, the P1, P2, P3 variables are all there, and I believe the 6-hourly output is there, and the others are coming soon. If you're a university researcher, I would highly recommend you do not try to download these from the NCAR Climate Data Gateway and instead get an account on Casper. And if you want to look at the data, just ask me where it is. So it's sitting on campaign storage on Casper, and we're happy to have anybody just access that directly. So we submitted a system description manuscript in April, and I'm also happy to share that. And the manuscript also goes over the large data volumes, and so you can get an idea what's there. The weekly forecasts are going to NOAA. We put them up on our FTP server every Thursday morning. If you'd like access to them, again, we can make it accessible. It's just a public FTP site, but it's not widely advertised. We just haven't had the time to do that yet. Yeah, so we would love for the community to get further involved in doing more analysis. And we do have a working group within CSM on our system prediction. So that's one way you can get involved in looking at the output. Okay, so for the last few minutes of my talk, I'll shift gears slightly and talk about the application of this research framework to the January 5th, 2021 warming. So it's funny, as we started the project of real-time forecasting for NOAA in September, we were hoping this would be the year where we get a sudden stratospheric warming or a reversal of the 60 north 10 hectopascal winds. These events happen on average every other year, but you could easily go 5 or 3 or 5 years without one. Very rarely, but you could. So we were very glad that during this testbed period for us, there was a warming brewing right around Christmas. So this is just a picture I pulled on Twitter, probably from Amy Butler's Twitter feed, that there was actually warming that came right on January 5th. And it was quite a big event. So we were interested to see how well WACM did with forecasting this. And why we care is explained by this figure from Amy Butler on the right, showing the surface temperature anomalies within 1 month after sudden stratospheric warming. So what you typically see is this cooling in northern Eurasia and warming in the United States. And especially the signature in Eurasia that's really there for almost every single sudden stratospheric warming. So we would expect that after this event as well. Okay, so firstly, how did we do catching the warming? And I think we did pretty well. So sudden stratospheric warmings are predictable 5 to 15, maybe sometimes 17 days out. So I'm showing you just different forecasts here. The top left is started on December 21st, and black line is observations from FPIT, the fast version of MERA. And the thick blue line is our ensemble mean, and the little lines are individual ensemble members. And you see on December 21st, one of our members had actually really well, and several other members were predicting a warming, perhaps some of them further on in January. Some of them maybe didn't quite predict the warming, but it was a weakening of the vortex, but we were on track on getting this. On December 28th, when we ran the forecast, you see a substantial number of members predicted the sudden warming, even though the ensemble mean did not. And it was lucky that we ran our forecast on Mondays. So January 4th, we ran our forecast and the warming came the next day. And this time the ensemble mean perfectly captured the warming. So, and then the recovery too. So we were really happy that the model was doing something correct in terms of capturing sudden warmings. And we reached out to Emerson at NOAA to provide us the week 3-4 forecast, and then we came up with verification for all the SubX models. So this is week 3-4 after the January 5th warming, so we're looking at the last week on January or so. And there are 2 models that did really well, and it had a correlation coefficient to the verification of 0.47, so 0.22 is the R squared. And those 2 models were ECC GEMS, so this is the Environment Canada model, and then WACM. And you can see this by eye. So if you look at the patterns, they captured most of the cooling over Eurasia. The warming in Eastern North America was captured by WACM, and that feature was captured by the GMO GS model, but just other aspects of the forecast were not quite right. So what we did further is try to figure out, and if you look at this pattern in WACM, it looks awfully a lot like the pattern from Amy Butler's paper of what sudden stratospheric warming should look like. So we were very excited. But we decided to run just a few experiments and repeat the January 4 forecast. And in the first one, we scrambled the stratospheric initial condition. So we only nudged the troposphere to observations and let the stratosphere evolve towards a climatological state. So we don't get very many sudden warmings there. Then we scrambled the tropospheric initial conditions. So only our stratosphere was realistic. And then we completely scrambled the atmosphere. Basically, we used an initial condition from a different winter which had a strong vortex and there were no sudden warmings. So here's a figure that illustrates that. So our standard forecast, we get a sudden warming, scrambled stratosphere, scrambled tropospheric initial conditions, half of our ensemble members had a warming. And these two last forecasts, the scrambled stratosphere and the scrambled atmosphere, had no resemblance in the stratosphere to what happened in real life. And this is what these forecasts for week 3-4 look like. And I'll bring your attention in the interest of time to this scrambled stratospheric initial condition one. As if you compare it to the standard forecast, it gave you almost the same thing. And however, there were no sudden stratospheric warmings in this model simulation. And the correlation coefficient squared to our original forecast is 0.79, so really high. So to make the long story short, from what we can tell with our model, with this particular case only, is that actually in January 2021, the week 3-4 anomalies that we saw at the surface really did not have all that much to do with the stratosphere. Most of the pattern was set up by the troposphere. There was a little bit of a contribution from the stratosphere, but it wasn't that big, and maybe partly maybe came a little bit later, but we only looked at week 3-4 at this time. And just this bottom left panel also shows you when you completely remove the memory of atmospheric initial conditions that your forecast scale goes to 0. So that again gives you an idea that the atmospheric initial conditions are really crucial to getting the week 3-4 forecast correct. Okay, so in short, summarizing, the S2S reforecast sets have been carrying out with CSM 2CAM6 and WACM and following the SubX protocol. There's lots of data available. If you like to get your hands on it, you can email me, or that's probably the best way, and I can point you to the data. The models are contributing to the operational week 3-4 outlook for NOAA. And we hope to keep using the research framework for other studies to isolate sources of predictability. And a lot of those experiments are planned through the Earth System Predictability Working Group that's part of CSM at NCAR. So thank you very much. And I think I'm out of time, so I will end here.
Thank you, Yaga. We have time for just 1 or 2 questions for Dr. Richter if we have them. You can put them in the discussion document. The link is in the chat. Or you can use the question and answer function of the webinar. Okay, while we wait for that, I'm going to make Dr. Liang a presenter. And Yaga, would you mind sending us your slides so we can post them later?
Absolutely.
Thank you.
And I'm not seeing the Google Docs, so if there's anything in there, if you let me know.
I will. I don't see any questions as of yet. But of course, if they come in later, we'll send the questions to you because I know you have to leave.
Great.
All right. Next we have Jinzhong Liang. And Dr. Liang, would you like to present your slides?
Hello?
Hello.
Yeah, I can, oh, now just a minute. Okay, let me, how to share my screen here.
Okay. I've made you a presenter, and what you want to do is look on the taskbar for a screen icon.
Can you see my? I couldn't see that. I'm sorry.
If you see your little webinar taskbar where it has your microphone and your camera icons, right under those two, you'll see a screen icon.
Yeah.
If you hit that.
Open System Preference Grant. Is that the one? Can you?
Just a sec.
For somehow just, okay.
All right. You see my screen?
Yes.
So you want to look for this icon here.
Oh, we can't see that.
Oh.
Mine doesn't show up.
Yeah,
I actually have the slides. I can show
Oh.
them if you just want to tell me when to.
Yeah, that's a bit good. I
advance?
couldn't see that for somehow.
Okay, sure. I can do that.
Okay.
No problem.
Thank you. All right, good. Okay, thank you very much. Thank you very much. This is analysis we are going on with. Actually, the results just came out for the simulation, and we wanted to show some preliminary understanding what the difference between coupled versus uncoupled GFS subseasonal forecast scale. This is jointly with Yaga's group, and we have next, please, next click. Hello? Hello? Yeah, so it's a bigger group working with. So what we are using for this analysis is the GFS is a prototype 5 model. So where the atmospheric model is identical with the GFS V15 and all GFS V12. And then we separated, we are going to analyze 2 different versions. One is the CPL, the coupled forecast. Another is the reforecast, uncoupled, the atmosphere only. And I just want to note that the 2 versions for the coupled one is the resolution is lower, about 50 kilometer than the forecast. So there have to bear these differences when we go through the analysis of the results. For some variables we assess is actually at a lower resolution even. So we finally decided to use 1 degree common grid to compare the 2 products. So we are focused on the 2 periods, experimental period, October 2017 to September 2019. And there are 11 members for each. So for all the analysis I'm going to present is averages these 11 members first. And then we separate the weekly by week. And we found that the week 1 and week 2, many signals we analyze is similar, and so also the week 3 and week 4. And that's the reason we group them together. And the week 5 have some signal, it's quite weak. So we are not going to talk about in this analysis. So what we are going to do is that focus on the differences. So we actually, after we did this 11 members, average we do the differences, CPL versus minus RFC, and you get these for each season. So each season you will have like 13 weeks with 2 years. So together, we actually for each of these seasons see a window we are interested in, week 1, 2 as a window, week 3 and 4. Then each of these windows we have 26 examples per season. So that 26 either we're going to average 26 for the seasonal mean differences, or we are going to use the 26 time series to do the correlation analysis. Next, please. So with that, there have already the group identifies the following key scale differences. So CPL has a significantly higher tropical scale. if we're using the 500 millibar height anomaly correlation to do, than the IFC. So throughout the 1 to 4 weeks. CPL also improved over IFC for the MJO scale at all read times, with the 50% anomaly correlation reaching 23 days for IMM1, the mode 1, versus the mode 2 actually even longer, can be extended to 31 days. The CPL largely reduced errors related to the ERA5 in surface latent heat flux and outgoing long radiation over tropical Indian to Pacific, West Pacific Ocean. And this area is actually the core of MJO key region, right? So this actually tend to enhance the predictive skill for convection activity over that area. So another one we need to bear in mind that the CPL produce warmer SST. This is slightly warmer than IFC. Their differences increase slightly with lead times and can reach about 0.35 degrees average over 50 north to 50 south, which actually it's about like a 2 watts per meter square differences downward radiation. So these seem to indicate a significant change from IFC to CPL in cloud radiation feedback on the subseasonal forecast. And when we actually now in the CPL, we have LC interaction turned on. So this will be feedback is through the cloud radiation, and we are going to focus on that area. Next, please. So another, like this is just a copy from the groups regarding how the performance is be conducted regarding 500, as I already described earlier. So what we are interested is that major skill job during, for example, January, May 2018 is related to the rapid ST change from negative to positive anomaly, which happened in observed, right? So the question also related to then would CPL perform systematically poorer in cold SST anomalies than in the warm conditions, and why? And then that one we still have not fully understand, but it's working on that. So next, please. So this is another slide we have been taking from the group analysis, show how the MJO is improving. And our question is that important here is how does the including LC interaction improve the tropical circulation and enhance the convection over Indian West Pacific? And again, we will using this this seminar to understand that portion. Next. So we're starting from the ST. So this is the ST difference. We call the surface temperature difference. Over ocean is ST, over land is surface skin temperature. So this is 4 different seasons. The top panel is winter, spring, summer here, and you can see there is a week 1, 2 average, and the week 2, 3, and 4 average on the right, and the week 1 and 2 on the left. So you can see quite strongly there is a systematic warm differences. CPL coupled one have a warmer ST than the IFC all over. Only in this West Eastern Pacific there is some cooling. So this next, please. So this actually is also see that the September is fall is the same. Next, please. So with that, then we began argument. What is the problem? What is the issue? Does the radiation act, or which is the driving force for this? So we started looking at first the net radiation. This is net radiation at the spot of the surface. So it's basically I try to starting with the energy budget for the SST first. So this is a radiation net, and the top panel is net radiation. The middle one is the latent heat plus the sensible heat flux. And the bottom is the total basic radiation minus the LSH, the sensible latent heat. So we see that there are differences is like everywhere is in the tropical region, most of that is radiation is negative. So less radiation into the surface, and the sensible heat is and the latent heat is more going out. But the net is about, for example, you can see about 10 watts per meter squares, but it's still negative. And this is it's for the winter time. And if you look at the next, please. Next, please. Okay, and you now see that the net radiation is negative. Just remember that. But then why the temperature is warmer? So this is certainly not the radiation is driving the surface. So actually the surface ST is kicking out more energy to the atmosphere. And we will come back to this later on. So now if we look at the other quantities, look at the outgoing long wave radiation here at the top, and then in the middle is a downwelling surface radiation, short radiation. That means not talking about reflection. Since the albedo we didn't change, it's only the coming back from atmosphere. And then we have also shown the precipitation at the bottom. So now you can see that with the outgoing long wave radiation in the tropical region, including the West Pacific and the West Pacific East, and also the Indian Ocean, is more long wave radiation going out, and the downwelling is less, and actually precipitation is more. And this also you can see is ITCZ actually in the tropical East Pacific also more shifted to the south. So these are actually getting signal is getting stronger in week 3 and 4. And particularly notice this is very cold. Okay, so text next, please. This signal is coming out, the same signal came out from the March, April, May, and you can see there a signal is moving a little to, for example, now emphasize more in the Western Pacific, but this in the Eastern Pacific is still remaining, and in the Indian Ocean now is beginning more, reverse the sign. Next, please. And the summer is the same, just a change around. But again, these major signals, how the OER, the downwave short wave radiation, and the precipitation response, they are very coherent. Next. And this coherence also occur in the fall. So, and actually the fall is now getting back to the Indian Ocean, becoming more, less OER and a less downwelling short wave radiation. Next. So now, while these differences occur in this radiation, but if we are looking at what the cloud is responding, it's amazingly that the cloud have a much more bigger signals in all of these. However, you can see that all the high-level cloud, low-level cloud, and the total cloud have a very large change. So this is puzzling me quite a bit. So because when you see these clouds, so big differences, we're talking about 10 to 20% differences. This is quite large. But then why they only specifically focus on certain area for downwelling and OER? So we will get into this point using the transient correlation to address this problem. Next, please. So now we're taking the differences. So what we are using is taking the surface temperature differences for each of the cases, 26 examples, and then do the correlation with other fields and to see how that actually related in transient sense. So the top one is again the radiation, net radiation at the bottom, at the surface, and the sensible latent heat. And here is the net radiation. So now it's very clear seeing that the correlation with the radiation is focused only in a very specific region, like as here is the Indian Ocean and the West Pacific. And this signal is decreased a little bit, quite a bit actually, in the week 3 and 4. But when you look at this latent heat and central heat, they are almost everywhere over the ocean is significantly correlated. I just want to say, mention that all these correlation, if it's not statistically significant above 95, we already use mask off, use white. So when you see these colors, this means that the temperature is slightly warmer. So the latent heat, actually, when you warm temperature, latent heat and central heat is always warmer to the, but that signal is only contained strongly in the first week, but then die off. But when you look at the net energy budget, then you see that it's everywhere is negative. What does this mean? So some energy, the energy is actually loosed from the ocean to atmosphere. So you need to some energy supply to maintain the ST still warming in the next 3 weeks, weeks 3 and 4. So this must be imply some heat transport, vertical heat transport from deep ocean, which we for now we do not have the data to analyze. But I think in the future we need to keep that to understand what is going on. So definitely this is one signal we are seeing. Next, please. So now this we go to the signal. Now it's very consistent when you do the correlation analysis here. OER is also focused this area, very similar, and the downwelling surface shortwave at the surface and the precipitation. Again, their signal is decaying down in the week 3 and 4, but still we have some signal in, for example, Pacific Ocean and also the East Pacific, tropical Pacific. And these are very consistent, telling us that more vigorous convection actually occur with the deeper convection precipitation enhanced. And also next, please. And this is when you get into the spring, the signal is actually amplified everywhere in the Indian Ocean and in the Eastern Pacific. And also all these, again, these signal is very consistent between variable. Next. The summer is weakening. Next. And the autumn is also weakening, but it's getting a little bigger than summer. Next. So another important signal I forgot to mention that the land is very different. So the land response is actually totally reverse than the ocean, particularly in the tropical region. And this occur not only just for these variables I just showed, but also seen in the convection. So now the cloud actual response is coherent with the radiation in this report. It's not like the whole band in the tropical region is higher cloud. And they are very focused on these regions which indicate that these deeper convection occur consistently acting on the radiation budget as well. Next, please. So with that, our main findings, please just click all these. So here. So the first is the systematic warmer STs seems to be primarily source for CPL scale gain, especially in the tropics. Warmer ST are likely maintained by upwelling heat transport from deeper ocean layers, which decreases significantly in week 3 and 4. So warmer ST increases the latent heat plus sensible heat, and the cloud also increases the cloud and rainfall and enhance the deep convection. This reduces OER and the downwelling shortwave radiation at the surface and a negative feedback to cool tropical Indian Ocean plus West Pacific Ocean. This is the opposite over the tropical land, where the convection tended to drive the surface. So significant differences also occur in Eastern Pacific Ocean, where responses are stronger in the means values. The mean differences we saw earlier, and such as Kodo ST, ITC shift south, more lower level clouds, and less downwelling shortwave radiation. And however, in the changing part, like the correlation portion, from weekly correlation portion is relatively weak. So answer related to the forecast skill are expected with notable change. This is my guess, but we could do that analysis later on. So I have a speculation here for this differences between the CPU and RFC. The convection cloud relation feedback under LC interaction plays a central role on MJO forecast. So initializing RFC with warmer ST to enhance deeper convection in the tropics may improve the MJO skill as seen in CPL. So if that's the case, that means we could show that our RFC, the uncoupled one, is actually probably the ST cool biases in the upward uncoupled one may be the reason for the differences we see how the CPL related to CPL. So that we will see. But I think my message is that we need to pay full attention to the convection cloud radiation feedback when we're talking about coupled versus uncoupled. Thank you.
Okay, thank you very much. So again, we have a question and answer document that's available to put your questions in, and that way we'll have a record of them. We do have a question. I didn't see who wrote it, but it says, could you clarify how you specify the SSTs in the uncoupled forecasts?
So the SST means that we're taking the coupled predicted SST and averaging in these weeks, and then compare with the same time the forecast, the live forecast, which prescribed SST with some perturbation on the SST. So initialize the one. So that's the differences.
Okay, any follow-ups on that? Any other questions? I'll go ahead and let's see. All right, since we're at the end here, I'll unmute everyone. So if you'd like to ask a question, you can unmute yourself. Okay, well, I'm not seeing any other questions. Karen, do you want to give us a preview of who's going to be speaking next month?
Yes, just give me one moment. Okay, our next webinar is going to be June 7th, and we will be having from EMC, both Avichal Mira and Arun Chawla will be talking to us. The first one will be on development of a coupled sub-seasonal to seasonal prediction model using community-based UFS for NCEP operations. And the second talk is UFS medium range weather S2S application code on GitHub and code management.
Great, thank you. So everyone come back to our website. We'll get the recording of this webinar posted after it processes, and we'll have the slides available. So we hope you enjoyed. And if you find yourself wondering about something from the talks later on, you can send us an email or go into our question and answer document and let us know that you have a question, and we'll see if we can connect you with our presenters. Okay. Thank you, and we'll see you next month.